So I wanted to do a second example of a type 2 problem, what I'm calling a type 2 problem. So type 1 is where you are given all the forces and you use the F equals ma to get the acceleration of the object. And type 2 is just reversing that. So we know what the acceleration is, and a lot of the times that acceleration is 0. And you want to figure out what an unknown force was. So that's what we want to do, and this one is a little bit more involved than the one we did in class, but it's not too bad. So we have a car with a certain mass, but it's on an incline this time, and this is the first time we're doing an incline. And it is kept from rolling down the incline by a chain that is connected to a wall up at the top of the incline. And we want to know what the tension in the chain is. So here's a picture of the situation. So the car is on the ramp, 25 degrees, and then here's the chain. Okay, so we want to make a free body diagram first. Here's the car. We identify all forces acting on it. We have gravity downward. We have the tension force, tension force. So the tension force is the pulling of the chain is pulling on the car. That'll be this way. And then we also have the normal force, because the car is sitting on a surface. And normal force is always perpendicular to the surface. So it's going to be going off. Oh, I wrote N here because I was thinking normal force. That's the tension force. The normal force is perpendicular, so it's going off, sort of slightly off to the left here. So here are the three forces acting on the car. Okay. The next step is to put a coordinate system on. Now, the usual thing, the thing we have been doing, is to just go horizontal and vertical. But I want to say that in this case, that's a bad choice. The reason that's a bad choice here is, although gravity is purely vertical, these two forces are both diagonal. And diagonal forces, as we're going to see in a second, we have to decompose them. We will have to use SOHCAHTOA and figure out how much of them is horizontal and how much is vertical. So we'll have to do that for two forces here. It's not going to affect this problem, but if the car was moving, the car would be moving along this line, right? So the car's movement would have both horizontal and vertical components. So that would complicate things as well. Instead, this is what I'm going to do. So let me take away those axes. I'm going to basically tilt my head and look at it this way. So this is my new horizontal and this is my new vertical. And I'll do plus on this side, minus here, plus here, minus here. Okay, and I am allowed to do that. I am allowed to set up my coordinate system however I like. The reason why this is going to be better in this case is, now notice that Ft and Fn are both in line with those axes. So Ft is now all horizontal, Fn is all vertical. Now gravity, we lost gravity, right? Gravity now is diagonal. So gravity is going to have two components that we have to figure out. But having one force that is, quote, diagonal, unquote, is better than having two forces. Plus, if the car was moving, now the car's motion would only have one component, right? So, again, that doesn't matter in this case because the car isn't moving. But if it was, that would matter. But even my first reason of just now two forces are lined up rather than one, even that is going to make this more pleasant to solve. So it's going to turn out that anytime you're talking about an object on an incline, that you almost always want to tilt your coordinate system so that horizontal is along the incline and vertical is perpendicular to it. That's almost always the right choice. Okay, so now I do have to do what I said, which is decompose gravity into a horizontal part and a vertical part. So it's going to be a horizontal part and a vertical part. Okay, so I have to break this down. Fg is the actual magnitude of the diagonal force. And so I have to break it down. So I need the angle. I need one angle on one of these right triangles. Now, up in my picture here, I have this. This is a 25-degree angle, and this is the way I think about it. Yeah, let's see. Use green. Original horizontal, like real horizontal, has now been sort of rotated up by 25 degrees, and that's my new horizontal, right? So original horizontal, tilde at 25 degrees, you got the new horizontal. Well, my vertical, here's real, a real vertical, and here's my new vertical. So if I'm rotating this 25 degrees sort of counterclockwise, then this also is going to get rotated 25 degrees. So this is 25 degrees actually, and down here, this is 25 degrees. All these angles are 25 degrees, sort of going from the original horizontal or vertical to the new corresponding horizontal or vertical. So for me, that angle right there looks like that's right here, right? That's this angle. So that angle right there is that same 25-degree angle. Okay, so that sometimes takes a little bit of practice to get. I'm rotating this whole coordinate plane 25 degrees counterclockwise, and although it's obvious right here, it's sometimes not easy to see where that ends up over here in the free body diagram. So I hope that helped a little bit, and with practice you'll get it. Okay, so then I can see, okay, this guy right here is the adjacent side, right? So that is Fg times cosine theta, because cosine goes with adjacent. And then this is my opposite side, so that's going to be Fg sine theta. But instead of writing it down here, I'll write it up on this guy, right? Those are the same. This is the other side of the rectangle. So this is F sub g times sine theta. Okay, so I have decomposed gravity into a horizontal piece and a vertical piece by using sine and cosine. Okay, so now I'm ready to do F equals ma. Horizontal, F equals ma. I've got tension in the positive direction, and I've got a component of gravity in the negative direction. And this equals m times the x component of acceleration. However, the whole point here is that I know, or I'm told, that the car is not moving, so it's certainly not accelerating. So that's 0. And so Ft equals Fg times sine theta. Just another way of saying that because it's not moving, this force and this force have to be counterbalancing each other. They're in opposite directions, and therefore they need to be the same magnitude to balance each other perfectly so that the car won't accelerate. The last thing I'll do here is just replace Fg with m times g. Okay. And actually, we're looking for the tension. We have it here. We have enough. Ft equals this, and we have all three of these things. Let me just quickly, well, here, let me finish it off then. Yeah, tension then, so it's 1,751 kilograms times 9.80 meters per second squared times the sine of the 25 degrees. And this is 3 significant figures. This one is 3 significant figures also. This one is 4. So I should put my answer as 3 significant figures, and it comes out to 7,250 newtons. So that is the magnitude of the force that the chain is responsible for. It's holding, it's pulling on the car with 7,250 newtons, which of course means therefore it's pulling on the wall at the other end with that same force. And the chain, if the chain can withhold that much tension in it, then it's fine. If that's more than the chain can handle, and this is a question for engineers who are designing the chain, then a link will break and the car will fall down, slide down. Okay. Now we're done the problem, but we could also have done vertical, and just for practice, let's also write down F equals ma for vertical. So with vertical, we have the normal force in the positive direction, and we have a component of gravity in the negative direction. This is the cosine component, and that's going to equal ma, but the vertical a. But again, acceleration is 0 all around here. So we get Fn equals Fg times cosine theta, which is m times g times cosine theta. So we could actually figure out the normal force if we wanted to from this formula. But okay, this problem is good. We have figured it out. Again, first of all, this is a good example of putting in acceleration 0 because that was known and solving for a force. That's what this problem was about. But also another good lesson that this problem is learning is to tilt your coordinate system whenever it is to your benefit, and it will almost always be to your benefit when an object is free to move on an incline, like this problem. Okay.